A chip the size of a solenoid executes billions of operations per second. How can such a heat flux be removed effectively? The answer lies in the structure and the manufacturing process of the heatsink. In the next 3 minutes, we will walk you through 5 mainstream cooling solutions, from extruded aluminum to liquid cooling. Let's begin with the most widely used type, extruded aluminum.
An aluminum billet is heated to about 480 degrees and forced through a die to form continuous fins. Due to process constraints, the fin pitch is typically no less than 1.5 mm, so the heat dissipation area is relatively limited. Its strengths are low cost and mature processing, suiting LED luminaires, home appliances, and low power supplies.
Denser fins and a larger heat transfer area are required. Scaled fin technology comes into play.
A cutter skives the surface of a solid aluminum block directly, bending the chips upright to form fins. The pitch reaches 0.3 mm, about 1/5 of extruded aluminum, with the heat transfer area increased by 3 to 5 times. Since the fins and the base plate are one piece with no welded interface, the heat path remains continuous. Typical applications include base station RUs, server CPUs, and variable frequency drives.
When the heat source is separated from the cooling position and the space is tight, solid metal no longer suffices. Phase change heat transfer is needed.
That is what a heat pipe does. The pipe is evacuated to near a vacuum and charged with a small amount of working fluid. At the evaporate end, the fluid boils and absorbs a large amount of latent heat. Vapor condenses at the condenser and releases the heat. The capillary structure then returns the condensate, forming a passive loop with no external power.
Its effective thermal conductivity reaches 5,000 to 10,000 watts per meter Kelvin or more, about 10 to 50 times that of pure copper. Note that effective doesn't mean the material itself conducts better. It is the equivalent effect of phase change mechanism. A heat pipe addresses linear heat transfer, but a large die dissipates heat across a planar area. For large dies, a vapor chamber can hold the temperature difference across the chip within 2 degrees. It is now widely adopted in premium smartphones, with typical thickness of only about 0.3 mm.
When power density climbs further and air cooling and passive solutions approach their limits, liquid cooling becomes the preferred choice. One figure is enough to demonstrate its advantage. Per unit volume, water's heat transfer capability is roughly 3,500 times that of air. Water is over 800 times denser than air and has over 4 times the specific heat capacity. For applications at tens of kilowatts, such as AI servers and data centers, liquid cooled plates are already the mainstream solution.
Having reviewed all 5 solutions, let's wrap up with a comparison chart. Choosing a cooling solution is essentially a trade-off across 3 dimensions: power, space, and cost. Back to the hot CPU from overview. After this episode, you should be able to match the right cooling solution to the power level and the application. Thank you for watching, and see you in the next episode.